Hey calculus students, here's another video for you. In this one we're going to review and talk about exponent rules and logarithm rules. These are things that we will use on a daily basis in calculus, and we certainly need to be very familiar with them. We don't want to get stuck and not be able to do a calculus problem because we don't remember some of the basics here. So let's start with the very basics. You know that if you see something like this, x to the n times x to the m, what does that equal? What does that simplify to? Think about that for a second. Maybe pause if you need to. That's x to the n plus m. Why? Why is that the rule? It's certainly good to know that that's the rule, but I think it's also very important that you understand why that's the rule. Well, we could take a simple example like x squared times x cubed and think about, well, what does x squared mean? X squared means x times x times x cubed. Well, x cubed means x times x times x. And then if we look at what we've got here, we've got a total of 5 x's all being multiplied together, or in other words, x to the 2 plus 3, or x to the 5. Right? That's why that rule is what it is. How about x to the n divided by x to the m? What you do with that? Well, that's x to the n minus m. Why? We could make another simple example here. Let's say x to the 5th divided by x squared. Well, x to the 5th is x times x times x times x times x divided by x squared, which is x times x. And know that we can, if we have multiplication in the top and bottom of a fraction, then we can simplify this by canceling things out. So one of those cancels out and one of those cancels out, and what are we left with? We're left with x cubed on the top. So 2 of these canceled out some of those, so that's x to the 5 minus 2, because 2 of those took out 2 of the ones on the top. That's x cubed. That's why. So those are very basic rules. I'm sure you know those. We should throw in, just for good measure, what's x to the n to the m. What about that? Well, that's x to the n times m. And why is that true? Well, we could do what's x squared cubed. Well, x squared is x times x cubed. And to cube something means multiply it by itself 3 times. That's x times x times x times x times x times x. That's what it means to cube something. And if we total those up, you can see there's 6 of them. And I think it's pretty easy to see, going back to what we started with, that, oh yeah, I've got 3 of these things multiplied together. So it's basically an extension of this rule, right? I have x to the 2 times x to the 2 times x to the 2, or 2 plus 2 plus 2, which is the same as 2 times 3. That's x to the 6th. Now, using those rules and extending them maybe into some not quite as obvious examples gives us the definitions of what a negative exponent is and what a rational or fraction exponent is. So let's try that and see what see how that goes. So let's say we had, for example, x squared over x to the fifth. Well, I know that if I wrote that out, like in the couple examples ago there, that means this, right? So 2 of the x's up here are going to cancel out 2 of the ones on the bottom. So that leaves, and I'm dividing these out, right? I'm not subtracting them away. So when I divide both of those out, the thing that's left behind, it's not a 0, it's a 1, right? When I divide both of these away. For example, if you had 2 times 3 and you divide away the 2 and you divide the 3 out, you're not left with a 0, you're left with 1. That's the sort of residue that's left behind when you divide everything away. And then here we've got x cubed, right? But also, by this rule right here, I know that x squared over x to the fifth, if this rule is supposed to work all the time, and we would certainly like it to work all the time, that means that x squared over x to the 5 is the same as x to the 2 minus 5, or x to the minus 3. So that means that x to the minus 3 must mean the same thing as 1 over x cubed. If we would like this rule to work all the time, and we certainly would, we don't want to have a little asterisk next to this rule and say, oh yeah, this is the rule, but it only works when n's bigger than m. We'd like it to work all the time. So if it's going to work all the time, then this must be true. So in general, that means that x to the minus n power means the same thing as 1 over x to the n. That's what it means. It has to mean that. Right. Similarly, what does x to the 1/2 mean? Well, maybe you remember what it means, but why? Well, let's see. If we did x to the 1/2 times x to the 1/2, then by rule number 1, our most basic exponent rule, that must mean x to the 1/2 plus 1/2, right? That's just an application of this rule, and that's equal to x to the 1, of course, and that's just x, right? So what does x to the 1/2 mean then? Well, x to the 1/2, if we multiply it by itself, we get x. So x to the 1/2 is the thing that when you multiply it by itself, you just get an x, which means that x to the 1/2 must mean the thing that when you multiply it by itself, you get x. And by definition, that's what the square root of x is. So x to the 1/2 must mean the square root of x. Likewise, what does x to the 1/3 mean? Well, 1/3 plus 1/3 plus 1/3 is 1. So what's the thing that when you multiply it by itself 3 times, you get x? Well, that's the cube root of x, by definition. That's what cube root means. The cube root of a number is the thing that when you multiply it by itself 3 times, you get x. For example, the cube root of 8 is 2, because 2 times 2 times 2 is 8. So that means, in general, here, that x to the 1 over n power means the nth root of x. And you know that when there's no number there, we assume that that means square root. It's like there's a little 2 there. That's the default meaning of that symbol. So again, these things aren't something that your Algebra 2 teacher just made up to torture you because there weren't enough rules otherwise. These things have to be what they are because of the basic rules. Let's see. So then what about x to the n over m what does that mean? Let me just do a combination of these rules then. By the multiplication rule, that's the same as x to the 1 over m times n, because n times 1 over m, right? By this rule right here, n times 1 over m is the same as n over m, which means that this, and now we know that x to the 1 over m, that's the mth root of x raised to the nth power. And whether I put that exponent out here, you could write it like that, but that's equivalent to writing it like this. So that's what that means. The denominator is what root you're taking, and the numerator is, well, the numerator is exactly what you would think it is. It's just a power of x. So, those are rules to be very familiar with. We want to be able to do comfortably, for example, if I asked you to do this, what's 27 to the negative 2/3 power? I want to be able to do that comfortably without the use of a calculator. Let's see. So I think the order that makes sense to do this is to do this first, and then this, and then the negative sign. So there's 3 different rules that will apply here. So I'm going to do 27 to the 1/3 first, and then I'll do the negative 2 part after. So 27 to the 1/3, that's the cube root of 27. That's 3 to the negative 2. And then I'm going to do the 2 part, and I'll leave a negative 1 on the outside. So 3 squared is 9. I still haven't done the negative sign. And then 9 to the negative 1, that's 1/9. So I think I would like you to be able to do this just looking at this and then go straight to here. And here's the thought process. 27 cube root is 3, squared is 9, flip it over, 1/9. Right? That's the order you would think about that in. All right. How about logarithms? There's a few logarithm rules that we need to be familiar with. So, if you have logarithm some base b, most typically our logarithms will be natural log, but could work for anything. So log base b of some number n plus log base b of some other number m. Well, if you remember what logarithms are exponents. So adding exponents, if you look back, these are all very closely related to here. When do you add the exponents? Well, when you're multiplying. Excuse me. So that's the same as log base b of n times m. And that works, of course, equality is a two-way street, so you can go either way there. Likewise, log base b of n minus log base b of m. Well, let's see, logarithms are exponents, so you subtract exponents when you're dividing. So that's the same as log base b of n over m. How about log base b of some number raised to a power p? How about that? Well, if you think about what it means to raise something to a power, that really means like n times n times n times n p times. And if you just applied this rule a whole bunch of times, that means you'd have log n plus log n plus log n plus log n p times. Or in other words, you'd have p of those log base b of n's. So that if you have an exponent inside here, that can come out to the front. It's really just an extension of this rule right here. All right. Maybe in addition to this, I probably should have done this first. Maybe it's a good idea to just talk about what does this mean? Log base b of some number a is equal to, and if you have a statement like that, like what's really going on here? Well, what this really means, a logarithm is an exponent. And specifically, it's the exponent that you have to raise the base to get that. So, well, here it is. We've called it n. So this is the same as saying b, the base, to the n power is equal to a. So this logarithm, this is the exponent that connects these two numbers. That power here, it's the power you have to raise this to get that. So some examples, if I asked you what's log base 2 of 8, well, it's the power you have to raise 2 to get 8. So 2 to the something equals 8. Well, 3 is the power you have to raise 2 to get 8. And that's a nice easy one you can do without a calculator. And you could do little ones that are a little trickier, like what's log base 25 1/5. What do you have to raise 25 to get 1/5? Well, let's see. You'd have to, first of all, take the square root of 25 to get the 5, right? The square root. So 25 taking the square root of that is the same as the 1/2 power, right? So you'd have to raise 25 to the 1/2 power, but that would get you 5, and this is upside down. So you actually have to raise it to the negative 1/2 power. Well, that takes some practice to get very comfortable with those, but I know you've done that kind of thing before. And you can see, I hope you can make a strong connection between what we're doing here on this page and what we were doing here with the exponents, right? Logarithms and exponents are two sides of the same coin, just like multiplication and division are two sides of the same coin. Who was this terrible person who invented this logarithm thing and inflicted this upon us, and why did they do it? Well, if you want to know the name of the person, John Napier, a fairly rare, famous English mathematician. Most of the famous ones are European, continental European, that is, or I guess after the Brexit thing, you can debate all that. I suppose they're still part of the greater continent of Europe. Anyway, lots of famous French, Italian, German mathematicians. Not as many English ones, but there's a few. So this Napier guy, anyway, invented logarithms, came up with this idea. But the idea, it's really a necessary idea, because if you have a situation like this, y equals 2 to the x, the problem here is, if you would like to solve this for x, we need to be able to get that x out of exponent land and get it down into the more civilized realm of not being an exponent, say. So the way we do that is you take the logarithm of both sides, and since we use natural log most of the time, I'll do that. Of course, you know you can do anything you want to an equation, so long as you do it to both sides. That will preserve the equality. Right? So I'll take the natural log of both sides. And then by this logarithm rule right here, that means the same as natural log y is equal to this exponent I can bring down to the front, x times natural log of 2. So x is equal to the natural log of y, or the natural log of 2. Or, if if you recognize this definition here, you could say, wait a minute, I can just take this and go straight to, okay, my base is 2, right? Log base 2, that's the thing that's getting raised to a power, right? It's equal to y, and this is the exponent. So x equals log 2, log base 2 of y. So this is interesting. I got two different versions of this, of what x is equal to. And that brings us just to our last logarithm rule, which is the change of base rule, that says if you have a logarithm base b of some number a, that you can change the base. And you can write this in a form where you can change the base to whatever you want. But since we are so biased in favor of natural logs, I'm going to give you the exclusive natural log version of the change of base rule. If we're going to change the base, then we're going to change it to natural log. And that right there shows us an example of that. That log base 2 of y, you say, well, that's the same as natural log y over natural log 2. Right? And this, the little bit of math that we did here, justifies why that rule is correct. So this is called the change of base rule. Why would you want to change the base? Because if you had log base 3 of something, for example, you don't have that button on your calculator. You don't have a log base 3 button. But you do have a natural log button. And you also have that LOG button, which is log base 10. But honestly, nobody really cares much about log base 10 once you get past, I don't know, 2nd grade or something. So don't worry about that one. Natural log's the way to go.